So we finally made it to 6.3, the central limit theorem. So the central limit theorem is incredibly important. So we started off with descriptive statistics. Descriptive statistics, where data was collected for us and we would describe it with things like mean and median and standard deviation and percentile, different measurements. We would analyze it. We might put it in like a histogram or something like that. So we were describing data that had been already collected for us. And then in the second unit, we worked on probability. We talked about basic probabilities. We talked about like ors and ands and complements. We talked about discrete probability distributions, the binomial distribution. We talked about normal distributions. So the central limit theorem is the kind of the climax of probability theory that connects probability with statistics and allows us to make inferences about data that we don't have yet. So we want to be able to do inferential statistics. So what's inferential statistics? That is the branch of statistics that deals with making inferences about data that hasn't been collected. So the central limit theorem is one of the key things that allows us to do a lot of the inferential statistics we want to do. We're going to do something called confidence intervals and hypothesis testing. And in the background, the central limit theorem allows us to do all that. So what do I want to do here? I want to be able to scroll. We want to state the central limit theorem. The central limit theorem, what does it say? So you have to understand what it says. So let's say you have a random variable x. What's a random variable? It's just some characteristic that takes on numbers. Let's say weight. Weight could be a random variable, or height could be a random variable. And let's say that the mean for the random variable, the average, is mu, and the standard deviation is sigma. So the mean is some number mu, and the standard deviation is some number sigma. So what we're going to do, we're going to take sample sizes of a certain size n. So n is going to be the size of your samples. They're going to take all the possible samples of that particular size. Now think about getting sample means. So you have all these samples of a particular size called n, size n, and you take all the sample means. So you're going to have a whole bunch of sample means for every single sample. So the distribution of sample means, so if you put those sample means all in a distribution, that sample distribution, that distribution of sample means, we call it a sampling distribution, is going to be approximately normal. For the larger size of n you get, the more normal it's going to look. So number one, the distribution of all the sample means will be approximately normal. That's the first big thing the central limit theorem says. So the bigger the sample size you take, so for example, if I took a sample size of maybe just 10, so I take all the possible samples of size 10. So that may not be very normal, but let's say we took samples of size 20, all the samples of size 20. Then all those sample means are going to be looking more normal. Then let's say, I don't know, we took a bunch of samples of size 100. So samples all of size 100, then the distribution of the sample means is going to be much, 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 much more normal. So the larger the size of n, let's say we took samples of size 1,000, n equals 1,000, then the sample means their distribution is going to be looking extremely normal. So the bigger the size of the sample you take, the much more normal looking your sample means distribution will look. So number one, you have an approximately normal distribution of sample means. Number two, the mean for that distribution of sample means, we call that mu of x bar. That's just going to be the original mean from the original population, mu. And the standard deviation for all the sample means, we call that sigma of x bar. That is going to be the original standard deviation by the square root of n. So let me say that one more time, just to give an illustration. So out here, let's say you're talking about GPAs. That's our x. That's our random variable, GPA. Let's say we're talking about GPAs of TWU students. So we know GPAs go from what, 0 to 4.0, right? 0 to 4. And who knows how that's distributed? So I'm going to put anything in green I don't know. So maybe this is the distribution. But this is not necessarily a normal distribution, the original distribution. So this is the distribution of x. So you'll know the mean, so the mean will be somewhere in here. I don't know, maybe the mean's like right here. And the standard deviation is going to be sigma. So that's all the given information. So you have a random variable, GPAs of TWU students from 0 to 4. You have a distribution, that's the green thing. The green curve is your distribution. Mu is the mean, standard deviation is sigma. So the idea is I'm going to take samples. Let's say I take samples of size, I don't know, 40. So I take 40 students from TWU and get their average GPA. 40 more students. I take all the samples of size 40. So you as a student will be in a sample of size 40. You'll be in many samples of size 40. You'll be in combination with all different students. So you and other students, you and other students, you and other students, all the samples you can imagine of yourself with other students. And we're going to calculate what's called the sample average or the sample mean. So we get basically a distribution of sample means. We call this X bar. So these are the sample means of student GPAs. So that's the average of 40 student GPAs. So you'll have lots of averages for every sample. And what happens is you're going to get an approximately normal distribution for these sample means, an approximately normal distribution. That's what number 1 says. You get that approximately normal distribution. Number 2 says that the mean of the X bars is going to be the mean of the original population. So the mean here is also going to be mu. That doesn't change. And then number 3 says that the standard deviation, which I call sigma X bar, let me write it this way. The standard deviation of the X bars is going to be sigma divided by the root of n. So that's different, right? That's the standard deviation of the original population divided by the square root of the sample size. So this is all for the sampling distribution right here that I'm circling. Now, let me circle that again. I'm going to circle it with a, let's put a, I don't know what color border, a purple border around this. Trying to put a purple, well, I'll use a highlighter. So this is my sampling distribution right here, surrounded in yellow. So we have a distribution of sample means. You see that red curve there, that's the distribution of the sample means. So the mean of all the sample means is mu that's in the center. That's the same as the mean of the original population. And the standard deviation for the sample means is sigma divided by the square root of n, sigma divided by the square root of n. So that's the central limit theorem. Okay, let's work some problems. Can I scroll? Yes. So in general, let me just put another note. In general, to use the central limit theorem, you need a large enough sample size. You need a sufficiently large sample size. So for example, let's say my original distribution, X, looks something like this. And let's say I take a sample size of 10. Sample size of 10. And I look at all the samples, every single possible sample from this population of size 10 that I can come up with, and I look at all the sample means from each sample. And I put them in a distribution. So these are called the sample means, the X bars. So this might get somewhat normal looking. But because I have a smaller sample size, it's not going to be as normal as I would like. Let's say I take that same original distribution where the random variable is X. And this time we look at sample sizes of, I don't know, 50. Sample sizes of 50. And then for every single sample that we collect a sample mean. We find a sample mean. So that distribution of sample means is going to be rather normal. Why? Because the sample size was big enough. So the question is, how big is big enough of a sample size? How big is sufficiently large to get approximately normal? So generally, the agreed upon number is, this is not always true, but generally statisticians say a sample size n greater than or equal to 30 is sufficiently large. That's the convention. So normally you want your sample size to be at least 30 if you want to get a good approximation of normality, a good approximately normal distribution. So if the sample size is not 30, basically we're not going to be very accurate with normality. So this is our first video on the central limit theorem. We are going to work some problems, I guess, in the next